All right, welcome to the last video in Chapter 4. This is section 4.5, and so you'll notice that the beginning part of Chapter 4 was all the graphs, and so we wanted to give you a visual interpretation of what sine and cosine and tangent and cosecant, secant, and cotangent all look like. Get an opportunity to practice the algebra principles of phase shifting, right? Shifting right and left, up and down shifts, and then introduce some other shifting that can take place, like amplitude adjustments and period adjustments as well. So really a nice algebra review in the context of trigonometry, so that's exciting. The simple harmonic motion, they needed to fit in somewhere, and this seemed a logical place for them. It is an important principle for physics and other hard sciences like that, where things move in a regular pattern. And so if we start here by looking at the definition of simple harmonic motion, it says the position of a point oscillating about an equilibrium position at a time t is modeled by either s sub t equals a cosine omega t or s sub t equals a sine omega t, where a and w are constants and w is greater than 0, or omega is greater than 0. I shouldn't call it w. The amplitude or motion is the absolute value of a. The period is 2 pi divided by omega, just like we knew before. That's why it's here, right? Because they can talk about period adjustments. And the frequency, which they sometimes talk about, is the oscillations per minute. It's simply just the flip of the period. So as odd as that is, if you wanted to know the oscillations per minute, it is omega divided by 2w. So the easiest way to think, and they'll have a good picture in your book about simple harmonic motion, is having a spring and maybe pulling on it, and has a weight on the end, and you pull on that weight and then let it bounce back and forth. It has some equilibrium point right in the middle, and it's oscillating back and forth, and this will give us the equation for it. You can think, well, why do I care about a spring oscillating? You don't, but you care about electricity, which it moves in waves, and you care about light, which moves in waves, and you care about sound that moves in waves. And so they will help describe a lot of things. But its simple picture that we can all understand is a spring, right? And so that's what the first example has. Really, this is nothing more than a formula being presented and you working through that formula and understanding it. And so you can look at this as something, oh, this is new and difficult. It isn't. It comes down to you reading through that definition and realizing that there's going to be a function that describes the motion, or the placement, a displacement, I should say, of the object. And we got to go and figure out what's being asked. So let's look at example 1 that's based on like number 4. A weight on a spring has an initial position s sub 0 is equal to negative 4 and a period equaling 1.2 seconds. Find a function s given by s sub t equals a cosine omega t that models the displacement of the wave. Okay, no problem. Here's some things that we know. Well, we need to fill in, so I'm going to just come in here and put in what we need to find in a different color. Apologize. Lost track of where my thing was. We need to find A. We need to find omega. Those are the two things that are needed in order to finish the problem. What is A and what is omega? Easily found. Let's first figure out A. So when we go to figure out A, what we need to do is realize that we know something. We know s sub 0 is equal to negative 4. What does that mean? That means negative 4 is equal to A, which we want to find, cosine omega times 0. Okay, well, remember, 0 times anything is still 0. Cosine of 0 is 1. Negative 4 is equal to A. we get A that quickly. And in fact, you'll be so comfortable with this, you'll know, oh, the initial condition is my A. It's very similar to what you did in your intermediate algebra classes as exponential growth and decay. That number out in front of the base being raised to a power, usually E being raised to a power, was the initial stuff. You didn't, once you saw what you initially had, you didn't go through any work to do that. You just dropped it in there. Same will be that case. So we just figured out A. We're halfway done. And so because I can, I'll use the eraser here. And we now know that A is negative 4. And so I'm going to come back in here and say, well, we now know this guy this far. Right? We absolutely know this is negative 4 out here. And so all we need is to solve for omega. Well, that's easily solved for too. To get omega, I'll do that over here. Let's go to where the period is. The period is equal to 2 pi over omega. Now you should not be surprised about that. That's what it was in the 4-1 and 4-2. It was the period of cosine 2 pi divided by the number in with the cosine, a number in with the variable that the cosine was operating on. This is not a new formula. It's the same one you used when you had y is equal to cosine 2x to know that the period was pi. So they haven't brought up anything new. The only thing that they told us is that the harmonic motion will follow this. So all we have to do is solve for omega, because we know the p is 1.2 seconds. So it might be best, 1.2 is 6/5 is equal to 2 pi over omega. I don't know if that's better, but that's the way I would do it. So 1.2 is 1 2/10, which is 1 1/5, which is 6/5. So I'll do the arithmetic in case somebody needs it. So a 6/5 is 1.2. You're welcome to use the 1.2, but then you have to put things in decimals, and I don't think that's the best. It's better to leave things as exact. So we're going to bring up the W and get 6. So I'll walk through this in case somebody says, Jensen doesn't show us everything. And then we'll multiply by the reciprocal. I was going to say divide by the 6/5, but I'll word it as multiply by the reciprocal. And you can see, oh, Jensen should do everything, 3. And so you can see that you have 5 pi over 3 is equal to omega. Now we're done. S sub t is equal to negative 4 cosine of 5 pi over 3t. Okay, if you don't have it as 5 pi over 3, you're going to have some rounded off decimal, and that's never good. It's never good for the rounding to take place before your end answer. And so if we can keep things exact, we will. So that's why I went to 6/5. I wouldn't have had that luxury, I don't think, depending upon the situation. Actually, I should. They would terminate, so I could always take some kind of decimal and put it into that. Now they want us to evaluate S sub 1. So S sub 1 should be easy. We're going to use a calculator because there's, well, maybe we can figure it out because we have things in pi over 3's. So S sub 1 is negative 4 cosine of 5 pi over 3 times 1, which is negative 4 cosine of 5 pi over 3, which is negative 4. And let's think about what the cosine of 5 pi over 3 is. Let's think. The cosine of a pi over 3 angle is always 1/2. 5 pi over 3, what quadrant is that in? That's in the 4th quadrant, and cosine's positive in the 4th quadrant. So we have 1/2. So hopefully you track that. So I'll show you the details. Here's 5 pi over 3. We use the pi over 3 reference angle. We have memorized that the cosine of pi over 3 is 1/2, and we know that all students take calculus. So I think every normal person would go through that. I don't think that there's too many people that just have all the angles memorized. They go off of the reference angle and what quadrant, and they can get everything that they need. So nothing earth-shattering, just our core trig coming out, be very careful. If you find that the only way you can figure out the cosine of 5 pi over 3 is to put your calculator in radians and put it in that way, be very concerned about your success in calculus. We need you to have these memorized. And so we get a nice -2 out of this. So S sub 1 is -2. That was part of the question. Then they want to know, is the weight moving upward or downward or neither at when t equals 1? At that one level, is it moving up or down or neither? Remember, this is probably why they're having us do this as a graph. Remember, at 0, it's -4. And the negative part of the answer doesn't tell us a single thing. It could be moving up or down. We need to figure out where that's happening. And so what we could do is we could graph it. We know that it goes through one full period in 1/6 of a second, right? So this is 0 or 1.56 6/5 of a second, right? And so we're a full second. So if it goes through one period in 6/5 of a second, or 1.2 seconds. So here's 1 second. Let's make that 1 second. So 1.2, it's here. So at 1, it must be on its way down, right? And going through here, because it's almost to 1.2. So it's on the downward trend because of what we know the period's got to be in there. In fact, I haven't even drawn it super correctly. It's a cosine graph, right? So, oops. Darn. That was not intentional. I apologize. Some good work that we're going to be doing a little bit later. Okay. And I think we are up here. That's the review. Yeah, we're right here. So I haven't even really done a great job of graphing that, and I apologize. I went to go get the eraser and clicked a different thing. This is the low value for it, right? And remember what cosine does. Let me not label something. It goes up to the 4, back down, right? And there we would span everything as we go through there and get our one full period. Well, at 1, it's down here. I'm sorry, 1.2, it's at the bottom part. So 1's back here. It's definitely on the downward trend because of how close we are to the period. So we would say downward. The other thing you could do is realize that from going from 1 to 1.2, it's got to fall down to the -4 in order to be at that same level, and so we must be going downward. So something to think about there. So the rest of the examples are pretty straightforward. They're just getting us to utilize things. So a note on a piano has a frequency of 110. Suppose the maximum displacement of the center piano wire is given by S sub 0 is equal to 0.11. Find constants A and omega so that the equation S sub t equals A cosine omega t models the displacement. Graph S in the viewing window 0.5, and so that's what's shown out here. I'm not sure why they're doing that. Maybe just so you could see what's going on. But here we go. We know S sub t is equal to A cosine omega t. We know S sub 0 is equal to 0.11. So we know that S sub t must be equal to 0.11 cosine omega t, right? That 0.11, the amplitude is going to be right in front. Okay, so we get a nice 0.11 there. And now we got to go through and sorry, I was just looking at something that's there. Now we got to figure out omega. So how are we going to figure out omega? The frequency is 110. So remember what the frequency is. The frequency is 1 over the period. It's the flip of the period. So that's going to be omega over 2 pi. So omega over 2 pi is 110. So that means omega is 220 pi. 220 pi is our omega. And so now we're finished. S sub t, sorry, two things going on there. Sorry, I did it again. At least I didn't go off of the page. So S sub t, we figured out from the 0 that it's 0.11 out front. Cosine, and we just figured out omega was 220 pi times t. Cosine of 220 pi times t. Done. Finished with that one. So it's just a matter of giving you a function and having you figure out what you need to know. It's really similar to exponential growth and decay problems that you've done in previous classes, most likely. An object is attached to the end of a spring, as shown in the figure. If it's pulled down a distance of 6 units from its equilibrium position and then released, the time for one complete oscillation is 4 seconds. So that's our period. So what did they tell us? They told us that when we start, we're pulling it down 6. And they also told us that our period is 4 seconds. Well, no problem. We're going to use our cosine again. So S sub t is equal to negative 6 cosine omega t. Well, what's omega? Well, 2 pi over omega needs to be equal to 4. So if we solve for omega, we're going to get pi over 2. Hopefully that's not too hard to follow. Multiply both sides by w, divide by 4. You're going to get 2 pi over 4, which is pi over 2. Simple type of algebra 1 manipulation, right? Beginning algebra. So what's our function? S sub t is equal to negative 6. Why negative 6? Because that was our initial position. I guess I should explain why we chose cosine. It's because at 0, cosine's 1, and I need it to be negative 6 at 0. So that's perfect. That's why I multiply by negative 6. If I use sine of 0 is 0, times anything is still 0. I wouldn't be able to have a starting position that's off of the equilibrium point. And so that's why cosine's used most often. So this is 6 cosine of pi over 2t. Awesome. Determine the position at 1.25. No problem. S of 1.25 is equal to negative 6 times the cosine of pi over 2 times, well, 1.25 is 1 1/4 or 5/4. That way we don't have to go to, we're going to have to go to a calculator. Look what number comes out there. Negative 6 cosine. I was hoping to avoid having to use a calculator that would be memorized, but we got 5 pi over 8, and we don't have any of our pi over 8s memorized. We'll learn a half angle formula, but even that's a little bit of overkill. We drop that into our calculator, but here's the biggest kicker. Everything that we've been doing in Chapter 2 and Chapter 7 was all in degrees. Remember, this is in radians. Change your calculator to radian mode when you have radians. Change it back to degrees when you have degrees. But if we take negative 6 times the cosine, and I'm in radian mode, I'm going to type in 5 times pi divided by 8, close my parentheses, I get a 2.296, or 2.30 would be its position. Find the frequency. Frequency we could have done right away. That has nothing to do with anything. Frequency is the reciprocal of the period. So it's 1 over the period, or by what they told me in the very beginning, 1 over 4. It's 1/4 is our frequency in there. And so it's 1/4 oscillations per second. Okay, so that makes a whole lot of sense though, right? For the time it takes to complete one oscillation, that last sentence being 4 seconds, that means there's 1/4 of an oscillation every second if it's the seconds that we're after. Okay, the period in seconds of a pendulum length L in feet is given by, and we have that formula there, right? This is number 14. It's not Wayne or Michelle or Lily, two of the colleagues that I have that helped me write this. It's a book problem, right? It's not something that we made up. And so we need to figure out how long should the pendulum be to have a period of 1 second. We can do that. Okay, so we need the period to be 1 second, and we'll be able to figure out the length because L is the length of that pendulum. So pendulums move in simple harmonic motions as well. No problem. What do you want the period to be? Well, you want the period to be 1 second. Plug it in. 1 is equal to 2 pi square root of L over 32. How many variables are present? 1. Solve for it. It's the actual one that you want. You want L. So what are you going to do? Maybe you'll divide by 2 pi first and have that equal to the square of L over 32. Then naturally you'd square and get 1 over 4 pi squared is equal to L over 32. And then you'd multiply by 32 and get 8 over pi squared is equal to L. So 8 over pi squared feet is equal to L. So let me come up here and just write the units. The length should be 8 over pi squared feet. So hopefully you know that you'd multiply both sides by 32, and that you know 32 divided by 4 is 8. That's where the 8's coming from, if that was confusing. I just ran out of room to show those small arithmetic details, right? Classes that are well before us, right? Well, not below us, but in the past. The position of a weight is attached to a spring is given to that after t seconds. What is the maximum height that the weight rises above the equilibrium point? Well, the maximum height is going to be the amplitude. The amplitude is simply the absolute value of A, which is 4. It's going to only be able to go up 4. What's the frequency? And period. Okay, well, the period, no problem. We know that from before. If we had the negative 4 cosine of 10t function back in 4.1, we'd be set. We'd know the period was the original period for cosine divided by the 10 that's with it. It's not going to be any different. So the period's pi over 5, and the frequency is the flip of that, 5 over pi. Done. When does the weight first reach its maximum height? Well, we need to know when this maximum height we determined was 4 from part A. We need to know when this happens. And you shouldn't be shocked at the answer, by the way. So we're going to divide both sides by negative 4 and get negative 1 is equal to cosine of 10t. I'm hoping that you know when cosine's negative 1, that would be at pi. So 10t is equal to pi. Do not put 180, because 180 is not a real number. Pi is a real number. So this is the reason why radians were needed, is because we're working in real numbers, not these arbitrary degree measurements. So 10t is equal to pi. So it's going to reach its maximum height the first time at pi over 10. It's going to reach it a lot, right, over and over and over again. But the first time is going to be at pi over 10. So no problem, right? Just relying upon our quadrantal angles from way back in chapter 1 or 2. And then we know that it's pi. 10t then would have to be pi. So get that. Calculate and interpret 1.466. Okay, so if you look at S of 1.466, you're just plugging it into the given formula from the beginning. They could have asked that question first. When you do, I got 1.997. So it's about 2 inches above the equilibrium point. So the equilibrium point is that middle point that it passes through and bounces equivalent distances up and down. It's 2 above that, 2 inches above that. Done. That's the work that's here in this simple harmonic motion section. So give it a shot, see how it goes, and we'll pick something reasonable for the exam. But essentially it's just formula manipulation. Don't look at it as anything new. They just want you to be aware of simple harmonic motion and try to tie it into and recognize how the closeness that it has to things that you've already done, like exponential growth and decay.